In this lesson, we're talking about tangents of circles. Now, as soon as you hear tangent, you should automatically be thinking about sine, cosine, and tangent, the trigonometric functions. So the first thing we're going to do is try to explain to you where this tangent function is coming from. So here I have a circle with a radius of 1. It's called a unit circle. And I have my angle of theta. And so if I just, for fun, find the sine of theta, it would be the opposite, which in this case would be BC, over the hypotenuse of 1, which would just be BC. Then I can find the cosine of theta, which would be the adjacent over the hypotenuse, which of course, since it's over 1, would also just be AC. And I can also find the tangent of theta, which would be the opposite, BC, over the adjacent, which is AC. But you'll realize that we already have AC and we already have BC. So realistically, you could rewrite the tangent of theta as sine theta over cosine theta. Now, this makes sense if we look at it with an actual triangle. So let's just use a 3, 4, 5. If I found all the trig functions, sine and cosine, if I found the sine of theta, it would be 3 over 5. The cosine of theta would be 4 over 5. Now, this is telling me that if I take sine divided by cosine, I should wind up with tangent. So let's take sine, which is 3/5, and we're going to divide 3/5 by 4/5. And you'll remember from fractions that you are supposed to keep this first fraction and multiply by the reciprocal, which would be 5/4. You can cross simplify, and therefore the answer would be 3/4. Now this makes sense because if I went back to the angle of theta and got the tangent of theta, I would realize that it is the opposite over the adjacent, which is 3/4. So this is just showing you where tangent is coming from and why it makes sense. Now that you know that tangent equals sine over cosine, you can understand some of these funny jokes. So here's the first one. It says that sine gerene over cos gerene equals tangerine. Get it? Tangerine. Now, since sine over cosine equals tan, you might just draw this on your wrist or on your skin or wherever and say you already have a tan because it's sine over cosine. And for the last one, let's just look real quick at a triangle. We'll just do a 3, 4, 5. It's telling me that sine of b, which in this case would be 3 over 4, divided by the tangent of b, which would be this would be 3 over 5, because the tangent of theta would be 3 over 4, and if I divide 3/5 by 4/3, what am I doing here? It's very late. Go back. Uh-oh. Uh, 3/5 times the reciprocal of 4/3, I can cross simplify 3's, and therefore I would get 4 over 5. But what else equals 4 over 5? Well, it would be the adjacent over the hypotenuse, and therefore the sine of b over the tangent of b equals the cosine of b, or cos b, Bill Cosby. All right, so let's talk real quick about tangents of circles. It's actually very simple. If a line is tangent to a circle if and only if the line is perpendicular to a radius. So again, we're talking about perpendicular lines. If you remember from a while ago when we did the circle notes with the candy, you'll remember that a tangent line touches the circle in only one point. This is called the point of tangency. And since there's an infinite number of radii in here, there will be a point when it is perpendicular. Since it's perpendicular, let's go ahead and use the Pythagorean theorem. We're going to justify and verify that these are actually tangents. So we're going to just try to figure out if 10 squared plus 24 squared is equal to 26 squared. If you go in here and square this out, this is 100. This is 576. And 26 squared equals 676. And so the left equals the right, and therefore, yes, it's tangent. Some of these can get a little bit tricky because it looks like you have enough information here, but you actually need to take this radius of 5 and swing it around so that this is also equal to 5. So now you would have 5 squared here plus 12 squared for the other leg equals the entire hypotenuse, which in this case is now 13. Go ahead and test this with the Pythagorean theorem. And so you see that it works. Last one, same concept. So take that 12, swing it around. And then let's go ahead and see if this works in the Pythagorean theorem. Okay, some of these can get a little bit tricky. There is a lot more algebra right now than what we've been doing. So let's go ahead. We always have to remember that this, where it touches the circle, is going to be a right angle. Therefore, this entire length is going to be your hypotenuse. So let's go ahead and square the legs. That's the easy part. And now we have to say that r squared plus 77 squared equals this entire length squared. It's not 49r, it's 49 plus r. And we have to square this entire quantity. So this would just remain r squared. This would be 77 squared, which is 5929. And then we're going to square out this quantity. So if you remember, let me write this so that it looks, this is probably how we did it last year. You do not just square r and 49. You have to square r. You have to multiply r times 49 and then multiply that by 2. So this would be plus 98r. And then eventually you do have to square 49. So this would be 2401. Now I know we're getting some very large numbers, but you'll see it works out to be very nice because these r squareds are the same on both sides. These will wind up eliminating each other. I'm going to take the 2401 and throw it over to the other side. So that means that 3528 equals 98r, and therefore r has to equal 36. This is the radius, so from here you could find the area, you could find the circumference, you could find a whole bunch of different things. Same type of problem, go ahead and try this one. I'll do the work on the screen as well. Okay, this next theorem I'm going to call the party hat theorem because it looks like the circle is wearing a little party hat. Since it's wearing a party hat, this hat has to stay balanced on your head, and therefore these two segments have to be congruent. So tangent segments that come from a common external point are congruent. It's a very simple theorem. You look at this problem, you have the party hat on the circle, so you very simply just set 3x plus 5 equal to 32, and then solve for x. 3x would equal 27, so x would equal 9. Same thing, the opposite sides of this party hat are the same. X squared would equal 49. X could equal positive or negative 7, but in this case, it can only equal 7. Here's an instance where there are multiple party hats. Remember, the opposite sides are going to be congruent. So let's take this 24 here, and we're going to make this side 24. This is 20. So therefore, this would be 20. Since that entire side is 32, that means that this little segment is 12, which makes this little segment 12. And you're looking for BC, which is the length from here to here. So this would just be 36. Same thing for this one. It tells you that ST is 5, QP is 2. And we're looking for SQ, which is the length of this entire thing. So take 5, copy it over here, take the 2, copy it over here. 5 plus 2 equals 7. Okay, this one's not too bad. It's telling you that OC equals 6. It also says that CP equals 4. And we're looking for AP, which is up here. Now, remember, we talked about all of the radii being the same. So we're going to take this 6 at OC, and we're also going to copy that here. Remember, here's your tangent, so that makes your right angle. And now you're just applying the Pythagorean theorem. 6 squared plus what squared equals 10 squared? That would be 36. So now the question is, what squared equals 64? And of course, the question mark equals 8. And we're going to do this last final one. This one's a little bit more difficult, probably the hardest one we've done on the notes so far. So it says that OC equals 12. There is a question like this on your quiz. It also tells you that AP equals 9. And we're looking for PC, which is right here. Now, again, nothing is going to change. All of the radii in the circle are the same, so you can still assume that this radius right here is 12. There's your right angle, and so now we have to write our numbers out in the Pythagorean theorem. It would be 12 squared plus 9 squared equals, and again, we don't know what this little segment is here from C to P, so let's just go ahead and call this X. Therefore, this entire segment from O to P would be 12 plus X. And we have to square 12 plus X. Now, in the other ones, it was nice because on the left-hand side and the right-hand side, you had X squared. In this case, you're not going to have X squared on both sides, so you are eventually going to have to factor these polynomials. So 12 squared is 144. 9 squared is 81. Go ahead and square this out. If you want to rewrite it to put X first, that's fine. I know a lot of you guys want to. That would be X squared. 2 12s is 24. And then throw your X on. And then 12 squared would just be 144. If you combine like terms over here, you'll see that this winds up being 225. That equals X squared plus 24X plus 144. Go ahead and take away 25 on both sides. So you're left with nothing over here. That's how we know we can factor. X squared plus 24X. And I'm taking 144 and I'm subtracting 225 from both sides. So that gives me negative 81. You're now looking for the factors of 81 that are 24 away from each other. I'll go ahead and tell you what these are. The factors of 81, I know you're probably thinking either 9 and 9, but the factors of 81 that are 24 away from each other are actually 27 and 3. So now it's just a matter of figuring out which sign goes where. This sign is positive, so therefore the larger of these numbers has to be positive. The smaller must be negative. Remember, this equals 0. I'm just bringing this 0 from the left-hand side over. Now, separately, both of these parentheses equal 0. So that means that in this case, x could equal negative 27. So x could equal negative 27, or x could equal positive 3. I'm not sure why I can't write on here. My pen just stopped working. But for our purposes, the only answer we could actually use would be x equals 3.